I'm going to tell you today is a brief story about for the past 2 or 3 years how our lab have been using tools such as viral evolution prediction model to fight mutations of SARS-CoV-2. Next. Yes, I want to start this talk with these 2 graphs, which describes how UK's response to COVID, which is summarizing the hospitalization as well as death due to COVID-19 for the past year in UK. The reason why we use UK is really, the UK did a wonderful job on detecting SARS-CoV-2, at least for that period of time. And immediately you realize that from this 2 graphs that how mutation is pressing such a great challenge for the infectious disease at that particular time. Because you immediately realize that for each year, there'll be 4 to 5 waves of SARS-CoV-2 infection led by different variants. And the underlying story behind this graph directly means that the immune barrier introduced by natural infection or vaccination is easily breakthrough by the new variants. Okay, so this is really a big problem. Yeah, so, and this graph is basically tells you how many strains we already have for the past 3 years. There's over 3,000 named variants. And this basically tells you how fast this virus, SARS-CoV-2, is evolving. And the real question or the real challenge is that this speedy evolution of the virus have outspeeded how we have been developing vaccines and especially antibody drugs. And the current situation of this will just continue for on and on. And for the next probably 10 years, we'll still face continuous reinfections of SARS-CoV-2 and variant effective antibody drugs or vaccines, which is the most powerful tools we can deploy, is still needed. However, the real big problem is that the clinical development is slow. Even for mRNA vaccines, now we don't need to do clinical developments, we still need 4 to 5 months to deploy them. And the virus is still evolving at a much faster speed than the current efforts that we're doing in vaccine development. So I want to give you a personal example of how viral evolution ruins clinical development so that you have a better understanding of this critical challenge. So back in 2020, as Fred told you, we went back to Beijing, and with Sunny, we had this wonderful and lucky 2-cell paper where we tried to use our expertise in single-cell sequencing to solve some problems for COVID. So we screened around 60 COVID-19 convalescents and found out around 300 human neutralizing antibodies. And we decided to make the 2 most potent ones to push for clinical development with Beijing, and whose name was DXP593 and DXP604. These 2 antibodies was really the star at that moment because they was really potent, and they passed clinical trial phase 2, but was unfortunately escaped by Omicron. So we probably wasted $100 million with Beijing on this. And the hurting truth is really that there's still several antibodies from this 300 collection. To date, is still effective against all variants. So the real question, if we sit down and think after this failure, is really how do you identify the most broad spectrum ones instead of the most potent ones from the very beginning? And this problem is really equivalent at that particular moment is how do you define antibody breadth for a newly emerged virus like SARS-CoV-2, where at that particular time, 2020, the only strain we have is wild type. And to me, after a lot of thinking, I try to connect this problem to if you can predict viral evolution for a newly emerged virus, then you can probably define antibody breadth based on predicted variant strains. So this is how things get connected. And for the past 2 or 3 years, we have been working very hard on this problem to make successful predictions for SARS-CoV-2. But the really starting question is it actually possible? So we have to review the patterns for evolution for SARS-CoV-2. So SARS-CoV-2 as a virus is a really true believer of the survival of the fittest. So how it survives is basically it generates a large number of random mutations, especially on the virus RBD, which is a receptor-binding domain for a spike protein, which binds to the human receptor ACE2. So it generates a lot of mutations on the RBD, it's not purely random, it has to follow 2 criteria. So first criteria is it has to maintain a high binding efficacy to ACE2. Otherwise, it's a suicidal mutation because it will reduce its infectivity. The second, which is most important after the prevalence of the SARS-CoV-2, is it have to escape human neutralizing antibodies. So when a mutation can maintain a good ACE2 binding, while at the same time scale out of antibodies, it can become a potential prevalent variance carried mutation. So by following this hypothesis, we had this very wild effort on developing a technique that if we can have a high throughput experiment to measure the impact of each mutation on the RBD, which is around 4,000 mutations because it's a 200 amino acid long, and each amino acid can change to 20 mutations, so roughly 4,000 mutations. And if we have a high throughput methodology that we can measure accurately the impact of each mutation on virus' ability to attach to ACE2, which is related to its infectivity, and also at the same time we can measure the impact of each mutation on virus' ability to escape antibodies, then we probably can build a model that predicts the optimal solution for the virus to evolve, which is simply ruled by maintaining ACE binding or maximize its ability to evade antibodies. So we had this collaborations were inspired by a great work from Jesse Bloom on the here showed on the top right, which is a graph summarizing how the RBD mutations affect the binding of ACE2, where the blue ones are actually the mutations that strengthens ACE2 binding. The red ones are basically the mutation that decreases ACE2 binding. So the idea is we don't want the red ones, but we want the blue ones. And the real problem is, can we actually obtain the graph described in the left bottom, which is along the RBD sequence, can we actually measure the impact of each mutation on how many antibodies it evade? The difficulty behind this graph is really, for obtaining this one, you only have to do 1 times 4,000 assays because there's only one protein for ACE2. However, we know that for one monoclonal antibody, it's not enough to describe our complicated immune response. We probably need hundreds, if not thousands, of monoclonal antibodies to faithfully describe our immune response to a certain virus. So we probably need to do 1,000 times 4,000 assay. So this is truly where the technical difficulties are. So for the past 2 years, we have been spending a lot of efforts developing this technique called high-throughput demutation scanning for antibodies, where she basically solved this problem by 1,000 times 4,000 assays. This is actually a very easy assay. We basically synthesize this 4,000 mutation libraries and put it into the yeast. What yeast will do, it will display the RBD you put in on the surface, and for each yeast, it will carry one single mutation for the RBD. And then you attach a magnetic beads to the antibody and do a negative selection. What it will do is will deplete all the yeast that can still bind to the antibody and left the escaped ones in the supernatant. And since it's a magnetic beads assay, you can do it on the 96 well plates, so in 1 week you can have 1,000 measurements for 1,000 antibodies. So it's actually a very high throughput assay. But the important stuff is what is the results. So the result looks like similar to on the right, where for each antibody, you have a collection of mutations that can enable the escape of this particular antibody. For example, this is Eli Lilly's first EUA antibody therapy. It's called COV116, which this graph here is describing all the mutations on the RBD. For example, on the 417 position, all the letters means the possible mutations that can escape this particular antibodies. And we can get this results, what we call DMS profiles, for 1,000 antibodies in 1 week. And this is such a powerful technology. Not only is it very good for infectious disease, it's actually a very good tool for researching antibody-antigen response, because what we can do to this is we can use this as a single-cell sequencing, similar to a single-cell sequencing result. We can do unsupervised clustering using this DMS profile for each antibody, and it will directly reveal the immunodominant epitopes for any given antigen when you give it to a human or a mouse as a vaccine. And it directly reflects that the antigen-antibody response is not a continuous scheme. It's actually, on the antigen, there's immunodominant sites where a lot of antibodies get generated, and there are sites that don't have any antibodies generated. And if you project it back into 3D space, you'll find out it's actually become a continuous domain here. And it's nicely, you can go around the RBD, which is the black protein, the white protein is RBD, and you can describe in very good accuracy the distribution of epitopes response to the RBD stimulation. But the important stuff is how do you use this data to do mutation prediction? And I really want to go through this process with you guys because it's really a simple model. So for example, we have this 1,000 antibodies isolated from a particular immune background, which is, at that particular time, an Omicron breakthrough infection. The infection variants were BA.5. So we isolated 1,000 antibodies from this particular immune background, and we averaged all the raw DMS profiles for those 1,000 antibodies. But the problem is, once you just do a simple average, you don't get any signals because it's messed up all along the RBD space. But as I said at the very beginning, the virus won't choose any mutation that sacrifices much ACE2 binding. So you can add weights for each mutation for regarding ACE2 binding and RBD expression, and suddenly you become a sharpened graph. So you can start to find out some patterns. Okay, some predictions is available. However, it's still not good enough. And another trick we can play is that since we have this 1,000 antibodies in vitrally expressed, what we can do is we can weight all those DMS profiles based on the IC50s or the neutralization potency against a particular variance for each antibodies. So what this will effectively do is we'll filter out all the contributions by non-neutralizing antibodies, which does not give pressure to the virus. So this will make the prediction much more cleaner. However, it's not good enough because we can see here it's still pretty messed up, and we cannot have a good telling of which kind of variants or what kind of mutation will finally beat all the others. And finally, the final trick that we can play is that after tracing SARS-CoV-2 for 2 years, we know that SARS-CoV-2, although it's an RNA virus, its mutation speed is pretty slow in nature. So we can be safely assuming that for each time the virus is mutated, it's only mutating one DNA sequence at one time. So what we can do is we can add a codon constraint and filter out all the mutations that requires 2 or more DNA mutations. And what's left is a very clean prediction for each site and what kind of mutation will happen that is most optimal for the virus to evolve under a certain immune pressure. But the key here is how accurate is this, right? So this is what we've been doing is a prospective prediction. So we published this prediction model as well as the results that we predicted for BA.5 back in September 2022. And this is on the right is how the real-world convergent evolution of Omicron BA.5 after September. And you can see immediately it matches very well because this model tells you that the most possible 3 mutations for BA.5 to evolve is 346, 444, and 460. And it was S, N, or K respectively. And on the left, you can see for the real world, also for the BA.5, actually sequentially gain 346 mutation, 444 mutation, and 460 mutation individually from different individual lineage, as well as XBB, which carries 490, which is also predicted. So this prospective prediction we published in September, which greatly matches with later on the real-world prevalence of BQ.1.1 as well as XBB. So this is for the first time that we demonstrated that it's actually possible to do a very accurate prediction on a single amino acid level, how virus will respond through evolution to immune pressure. And this is basically the work that wins us the Nature's 10 back in 2022. And this prediction model has been widely applied internationally for genomic surveillance. For example, for the CDC in South Africa, when they sequence a new variants with 4 new mutations, and they don't know what to do with it, they can just plug in the sequence to this model, and the model will automatically calculate and tells you, okay, what does this 4 mutation do? How much ACE2 binding has it strengthened or reduced, and how many antibodies evasion had it introduced. And this is a great collaboration with Jesse Bloom and Cornelius, and has been now a daily tool for variant hunters as well as the global CDC. And as I said at the very beginning, the reason why we wanted to do this viral prediction is really want to make better drugs and vaccines. So we kind of want to try this whole stuff again, although the first time was a big failure. So we started again to isolate 1,000 antibodies from a particular cohort, which is a SARS-CoV-1 infection. So basically, those people have infected with SARS-CoV-1 back in 2003 and was given SARS-CoV-2 vaccination back in 2021. and we isolate all their memory B cells, and we expressed around 1,000 monoclonal antibodies, and did this DMS screening for every antibody, and selected one for clinical development, which is named as SA55, in collaboration with SINOVAC. And here is basically the global antibody development from Eli Lilly and Regeneron, and you see all their antibodies are already escaped, except for us. For SA55 is now the only one left for that is effective against the newest variants, including EG.5 or BA.2.86. And it can even neutralize SARS-CoV-2 and many sub-eco viruses. And the reason why SA55 was selected from this 1,400 collection is really behind the change of logics that we screen for antibodies. Before we screen for the most potent ones, but we have already proven it's not a good strategy. Instead, you have to screen for the most broad ones. So the reason why we select SA55 is really by doing this DMS screening, we know that SA55 is only escaped by 2 mutations, one on 503, one on 504. And from our prediction model, we know that there's no immune pressure on 503 or 504 whatsoever. So basically, choosing this antibody is a very safe choice. It was very hard on the population level to have a variant carrying 503 or 504 mutations that can circulate among population. So this is really the reason why for 2.5 years already, this antibody is not evaded. So we have been pushing this hard for clinical with SINOVAC. We have this injection, SA55, which is a really good drug. It was designed for high-risk population. It is aimed for long-term prophylactics for immunocompromised people who cannot take vaccines. Because after engineered, an antibody injection can live long as 80 to 90 days and can provide a half-year protection. We're also collaborating with Moderna trying to give an mRNA form of this antibody directly to human for using mRNA vaccines to directly give into it. It will be much cheaper and much easier to use. It also can serve as therapeutic user for immunocompromised people, especially for those that has rebounds or restriction use like of Paxlovid. And we have been using this drug for treating over 2,000 elderly patients in Beijing during the last outbreak, terrible outbreak in December, especially for those that had rebounds or restriction of use of small molecule drugs. We also have this pretty novel way to give it, which is through a nasal spray. It's designed for a normal population, which a very small amount, very cheap, and you just give it spray to your nose, which provides a very short-term prophylactic, 2 to 3 sprays per day, especially for the days that is very important for you. You really don't want to get infected. And one spray can protect 8 to 12 hours of protection and gives a high neutralization titers in your mucosa. And has been cumulatively used in China for over 200K individuals, although it's not already approved, it's the EOA usage. And it provides in clinic around 80 to 90% protection against symptomatic infections, which is by now the most effective way to prevent infection. But the real challenge lies ahead is vaccines. So for antibodies, as I said, it's easy because we just need to choose an antibody that avoids all the predicted possible mutations. However, for vaccines, if we really want to do this correctly, we need a very accurate ones. So are we ready for this? So I serve as well for the WHO to decide every year's vaccine composition for SARS-CoV-2 vaccines. So in May this year, we meet and decided to have a monovalent XBB-based vaccines. It was really a consensus that this decision is not the optimal solution. It's only a practical solution. It's really because the graph on the left, which here is so-called antigenic cartography. For those who are not familiar, it doesn't matter. Basically, just we have to remember that the more distance between 2 variants means the less cross-reactivity between the 2 variants. So what this graph tells you that the XBB vaccine here will have a very large distance to the circulating variants now. And for each graph means a 2-fold decrease in efficacy. So now the circulating variants already has a 4-fold decrease in efficacy in terms of preventing infection. So what this means that when we have a recommendation in May, where the United States has deployed mRNA vaccine using XBB in September, now it's already be decreased by 4-fold due to natural evolution. So the current way of updating SARS-CoV-2 vaccines will always be running behind natural evolution because the speed of SARS-CoV-2 evolution. And the real new strategy behind this is instead of using natural antigens, we use vaccines designed based on viral evolution prediction. But the real problem is how do we prove we are good enough, right? So fortunately enough, we can do this retrospective study where we, based on the antibody prediction model we have for wild type and for BA.5, and design vaccine boosters back then and to check how well the blood or serum can neutralize the current variants. So this is what we have been doing. For example, we have this 600 monoclonal antibodies isolated from wild-type convalescents. We got it back in April 2020, and this is how we predicted for wild-type to evolve. And immediately you can see several of the biggest prediction is E484K, which is the mutation carried by beta as well as by Omicron. And once you have this, you select this mutation, then you recalculate the antibody weighting, and for the next one you can pick is 417N, which is carried by beta and as well as Omicron. It's still in Omicron right now. So by doing this kind of simulation and iteration for 1,000 times, we calculate what is the most possible combinations of mutation that is possible generated by the prediction of evolution. And we use that as the vaccine strain. And so this is the kind of the result. For wild type and for BA.5, we have this bivalent vaccine design which contains the most probable possible mutations predicted by our evolution prediction model. And I want to emphasize that this design can be attained as soon as April 2020 if we have the technique ready at that time. And for BA.5, it is last June 2022. And this vaccine composition will provide much broader response compared to just use wild type or BA.5 as the vaccine booster at that time. So now we are also pushing this forward with the collaboration with Moderna and as well as many companies in China. And hopefully for next year or the next year, we can have mRNA vaccines deployed based on our design. So finally, as the time is limited, I want to give a summary. So I'll tell you today that actually a SARS-CoV-2 prediction model can be built on the integration of measurements experimentally, the mutational impact on ACE2 binding as well as antibody evasion. And it can be used for many other infectious diseases as well as even for cancer vaccines. The model can accurately infer for immune-evasive SARS-CoV-2 variants in advance for better preparation of antibody drugs and vaccines. And instructed by this model, we have the most broad spectrum antibody to date, which is SA55, identified, which is now in clinical phase 3 in China, and we can actually design vaccine boosters based on the prediction model, and it's very effective and promising. And at the last, I want to acknowledge Sunny especially for his help and supervision, as well as the support from Trumping Laboratory, and as well as the fantastic students in Peking University, for Fan Chong, who did all the viral evolution work, and Ai Jiang for the host immunity stuff. Thank you. Questions?
Thank you.